next talk is going to be given by Stephanie Weirich on algorithmic conversion with surjective pairing, a syntactic and untyped approach, and Yiyun will join us for the Q&A.
Okay, great. Thank you. So I want to start off by talking a little bit about my title slide, and especially my co-author, Yiyun, who is unable to come to POPL this year. So I am giving the talk. We're co-authors, but I would say about 99% of this work is his, and 1% is mine. And Yiyun, he is my PhD student. He is just now finishing. He'll be defending his dissertation next month. His dissertation concerns the dependent calculus of indistinguishability. This is this idea of adding dependency tracking to a dependent type system. And he's published in the past 2 POPLs, he's published 2 papers about decoy as a type system for a programming language or for a type theory. And in this work, we're kind of really trying to extend, this work is not about decoy, but it does enhance the expressiveness of the language. So just a little ad for his forthcoming dissertation, and Yiyun will join us for the Q&A session at the end and correct all of my mistakes. Okay, so let me go back to my title slide and try to explain what this work is about. So I'm going to be talking about conversion in a dependent type theory with surjective pairing. And what do I mean by that? So just to remind you, when you have a type theory, when you have a dependent type system, you really care about when types are equal to each other, right? You need to define what it means for type A to be equal to type B, and your type theory allows you to kind of work implicitly up to this equality, right? And because types contain programs, that also means you're trying to decide when programs are equal, and you want this to be as coarse a relation as you can get, because the more things that are equal, the more programs are going to type check, right? This relation for your conversion relation, your definition of equality, you want it to be a congruence relation, all the good stuff, reflexive, symmetric, transitive. You want, if all the subterms are equal, you want your term to be equal. You also want it to kind of reflect the computation rules of your programming language. So you often have the beta rule, so application of a function, projection of a tuple. Sometimes, and some dependent type theories differ, sometimes you will also have eta rules. So it's common to have the eta rule for functions that says that, if you have a function that takes an argument and immediately just passes it off to another term, that's the same function. Surjective pairing is another name for the eta rule for products, right? So if you have a term A, you project its first component, you project its second component, and you just put them right back together, that's the same as A, right? So that's the eta rule for products. Okay, so we want to talk about conversion with surjective pairing. We also want to talk about algorithmic conversion. So what is that, right? So what I showed you before was defining when types are equal, but that didn't tell you how to decide that. If you write a type checker, you need to implement a decision procedure, right? So the simplest decision procedure, this is kind of a sketch of it, right? If we want to decide whether A is equal to B, we just do some reductions. And if we get to the same thing, they're equal to each other, right? I call this reduce and compare. I really want to point out that this is actually a family of algorithms. You can reduce anywhere inside any term at any time. There was an absolutely beautiful paper yesterday about figuring out the right way to do it and doing it concurrently so you can actually do this efficiently. I'm being very theoretical here. We're just going to be talking about this sort of very general idea of an algorithm. Right, but this is a way to decide that. And for just beta equality, it works very well. right? And so how do we know it's correct, though, right? We're implementing our type checker. We have this definition of equality. We want to prove that we're actually implementing that language, right? And so to prove that this algorithm, if this algorithm decides that they're equal, our definition is that they're equal. To prove that it's correct, right, we need to know that that algorithm terminates, that we always return an answer. We usually do it with maybe a logical relations argument to prove that termination. We need to know that the algorithm is sound, that if it decides that two things are equal, then they actually are equal. That's usually a pretty easy proof to do because all of the steps that the algorithm does, they correspond almost directly to rules of our definition. So we can almost just read off that soundness proof. And we also want to prove that it's complete, right? That if our definition says that two things are equal, then our algorithm will find it, right? We'll decide that. And that's generally straightforward, but it can get a little bit difficult because our definition includes transitivity. And so we have to prove that this thing is transitive. And so the general way to do this often is to show that reduction is confluent, that it doesn't matter which way you go, you can always get to the same place. Okay. So all the stuff with beta reduction, that is all very classic lambda calculus stuff. You can read about it in Weirich's textbook. What about eta reductions? What about surjective pairings, right? And so if we want to extend our reduce and compare, we might think about adding, this reduction and that reduction, right? And we want to extend our proof of correctness to include these new rules, right? Unfortunately, we run into some difficulty when we get to surjective pairing, right? Because if you remember, part of our correctness proof relied on this confluence proof. And if you throw in surjective pairing, you can't really show that this reduce and compare algorithm is transitive, right? And so we don't really know how to do our correctness proof in that situation. Okay, so I'm just motivating the problem so far, but let's keep talking about the title. Okay, so we're thinking about algorithms for conversion with surjective pairing. What about untyped? What do I mean by that? So actually, when you look at the type theory of dependently typed languages, there's two approaches that people take. Sometimes they use the conversion rule that I showed you at the beginning of the talk. Sometimes they use a typed relation for equality. So they define what equality means, and that equality, that relation, it really has this precondition that we're only trying to relate things that have the same type. Whereas the original version I showed you doesn't really care, right, about what the types are. It's just oblivious to the types of its arguments. It's a bit controversial. People have very strong opinions about which dependent type theory should have. I'm not going to try to resolve this controversy in any way, even though my title says untyped in it. What I do want to do is kind of compare them a little bit, right? So in an untyped equality, right, if you're adding eta rules to an untyped equality, a lot of times you'll see this eta reduction that we've seen, but we don't have. There are other ways, but a lot of times you'll see things like this, but it will only be function eta. You won't see the surjective pairing because of that confluence problem we just saw, right? Whereas if you go over to a typed equality, a lot of times the algorithms will flip things around because they have the type information around, because they know they're only working with well-typed terms. They tend to work with things like typed eta expansions, right? And as a result, they don't need this, there's a different kind of algorithm, and so they don't need this confluence property that they don't have that confluence problem that we have. And so they typically do include surjective pairing as part of their type theories. And in fact, they even go further and they include like an eta rule for unit, which you really need to have the types there to be able to say that I know this term is, that I know that anything has type unit is equal to anything else of that type, right? And so, so many people might prefer typed equalities for that. I just want to point out, and why untyped equality is in our title, untyped equality is more extensible to certain kinds of irrelevance independently typed languages, where you want to say things are equal to each other, and they don't necessarily have the same type. This is what happens in decoy, and so that's how this talk is related to decoy, right? So we really want to have, in decoy, we're really forced to stay in this untyped equality, but we would like it to be as expressive as possible. We would like it to be able to have things like the surjective pairing rule. I don't think we will be able to have like the unit eta rule because you don't have types, right? But the products, yeah, it should be possible. Right? And so that's what we do in this paper, right? So in this paper, what we do is we show that the reduce and compare algorithm with eta reductions for products or functions and products is correct for both untyped equivalence and typed equivalence, right? There is a small asterisk on this slide. In order to do this, we have to solve a problem with confluence. In order to solve that, we have to change the specification of untyped equivalence just slightly to make it all work out, and I'll get to that, right? But what that does is it allows us to have this additional reasoning property in our type system. Okay, so how does it work? Right, what's a high-level overview of what's in our paper? So first we have to prove termination. Again, that's just the logical relation that we've done before. We also need to prove completeness. And again, we had this, for completeness, this is where this lack of confluence problem came into play. We solved that problem by, instead of trying to prove confluence for all terms, we're going to prove it just for terms that are in a good set. And then we're going to go back and prove that all well-typed terms are in this good set, right? And so if we can find a good set that has this property, then we'll be done. And then we'll prove soundness. So for soundness, for the untyped definitional equality, we'll be able to prove it's sound because we'll be able to use our confluence property, but we will have to restrict our transitivity rule. So with transitivity, you're saying that A is equal to C if in the case where A is equal to B and B is equal to C. That B, you don't know that it type checks, but if we don't really know anything about it, what we're going to do, that asterisk, is let's restrict that B to be a term in whatever good set that we have, the good set that we know things about. And then for the soundness for our typed equivalence, we have another problem that we have to face to deal with this, right? Because we're proving the soundness of typed equivalence with our reduce and compare algorithm, right? We're still doing reductions. The problem is, and this is really crazy, that there's a case where eta reduction is not type preserving. And so that's not going to work, right? So that can make soundness really challenging to prove. And so what we're going to do instead is that there are lots of algorithms out for typed equality that have been proven sound, that are based on expansion instead of reduction. We're going to find that algorithm. It's easy to prove it's sound for type conversion, and then we'll prove our reduce and compare sound with respect to that algorithm. All right, and so kind of go a little bit indirectly. Okay, so let me go back a little bit back to that completeness where I said that we needed that good set that we can prove confluence for, right? So our completeness argument needs this confluence proof. Our good set, we didn't invent this. We went and found, Yiyun went and found it in the literature. He found this set called SN. What SN is this is an inductive characterization of terms that are strongly normalizing, right? You're just writing the relation that just captures all strongly normalizing terms, right? So if you just sit down and write that out, you can define it as an inductive relation. And it's a really nice relation, right? It doesn't say anything about types, but it also doesn't include any stuck terms. And since it doesn't include any stuck terms, then that kind of it rules out all the bad cases of your confluence proof. Right? And so you can prove confluence for all the terms that are in this strongly normalizing set, and you can also prove that all well-typed terms are strongly normalizing. Right? And so that's our good set that we're able to use. And one thing that is surprising to me is like if you're creating this inductive characterization of strongly normalizing terms, of course it's going to tell you what all the beta normalizing terms are. But it's also telling you what all the beta eta normalizing terms are too. That just kind of falls out for free. Okay, now the other part that I talked about was for typed equality. Right, if we're doing reduce and compare, we had the challenge that not all eta reductions are type preserving. And so in order to get a soundness result for typed equality, we go via this algorithm called Kokan's algorithm. And Kokan's algorithm, it uses eta expansion instead. Eta expansion is always type preserving. And so we can use existing results that Kokan's algorithm is sound. And then we just have to prove that reduce and compare implies. So if two terms are identified by reduce and compare, then they're also identified by Kokan's algorithm. Okay, so that's almost the entire title. The last word of the title I want to talk about is syntactic. Right? We've done all of this work using syntactic methods, a syntactic approach. And what do we mean by that is we've been trying to reason as much as possible about the system just in terms of its judgments, its definitions in terms of functions and judgments, instead of in terms of models. Right? This doesn't restrict what kind of type theory we can work with. So, of course, the type theory I've been telling you about has functions and pairs, but Yiyun wanted to make sure that it was very extensible. So he also added in natural numbers with an induction principle to make sure that having an inductive type around doesn't destroy all these properties that we have just talked about. He also put in an infinite predicative universe hierarchy, put in subtyping just to make sure that it's a full-featured type system. Since we're working with a syntactic approach, this reduce and compare algorithm, it's a certified program. You can extract it, right? All of these syntactic properties are properties that you would want to have when you're implementing these things. I'm not sure you would actually want to run this. I would use a much more efficient convergent algorithm. But the thing that's really nice about these syntactic approaches is they don't really ask much from your proof assistants, right? We're not relying on a lot of libraries. We don't have a lot of logical strength in our system. The really only key thing that we need is automation for variable binding. Just like in Damian's talk, having the right decision procedure, a tool to help solve your problem can be very key. And in this case, for this particular situation, it was AutoSubst, the AutoSubst OCaml tool. Right, so our proof is about 10,000 lines of code. Of that 10,000 lines of code, it's mostly very syntactic reasoning. We do have a logical relation where things start to get a little bit more like a semantic proof. That's only this little red part here. Like this particular blue part, that's the confluence proof. It actually doesn't really even care about what the type system is. It's just agnostic. It's just doing properties about lambda calculus terms. And then this big dark blue part is a bunch of syntactic properties about the type system itself. Okay, so let me just conclude. We can include not just eta equivalents for functions, but also eta equivalents for products in our dependent type theories. It doesn't matter whether we have an untyped relation or a typed equality, right? And in our implementation, it's correct to do it with these reduction-based mechanisms. So we have some future work. We've made these definitions to be convenient for our proofs. There is some work still to make them more similar to the actual specification that you might see in Rock or Agda or Lean, but we're very confident that that could be done. And we've done this all in the context of just a vanilla dependently typed programming language. There is some work to integrate it into decoy itself. And of course, you can always make your proofs better and shorter and more automatic. Okay, so I'll stop here and open for questions, and hopefully we can get Yiyun to join us.
Sound working? Yes? Okay. Questions?
Hi, thanks for the talk. Do you have any specific ideas as to your very last point? Like, what do you think would be nice automation to have or things to do? And like, you have any ideas there?
I guess when you say automation, do you like refer to any specific parts of the mechanization, like overall, or
That's kind of my question, basically. Like, where do you think you could make we could make the whole thing kind of neater and easier? What sort of tools we could build, basically?
So I think So I'm not sure if how you describe this kind of problem. I think it's like more or less similar to the expression problem. If you have seen the slide, the previous slide that Stephanie showed, there's like 3,000 lines of code just for the confluence proof alone. And if you look into the source file, you'll see like there's these like different variations of the same type of reduction, like parallel beta reduction, weak head reduction, and then the same variance for like eta reduction, and the union of these two reduction relations. And then if you take all the combinations, you get like more than 10 reduction relations. Even though underneath there's like these two like beta eta reduction rules, you're just taking like congruence closure in different ways. So I think any type of tool that allows you to like describe these different variants very succinctly and then have this automation tactic that allows you to do the same kind of proof only once, but apply it to all the different variants. I think that would at least greatly simplify the confluence proof at least. I think in terms of logical relation, in our specific development, there isn't much to do. Like, it's already quite short. Although there is this thing where we use like Rock's prop to encode partial functions. Like, there's no induction recursion in Rock. And working with like partial functions, like encoding partial functions as an inductive defined relation is kind of tricky. Like, Rock doesn't know that it's actually a function underneath. So I know there's some work that allows you to like specify these functions in a nicer way. That kind of automation, I don't think it's going to like reduce the lines of code that much, but it will make the proof much more pleasant to work with, especially when you have to do like Kripke style logical relations. Yeah. Hope that answers your question.
Hi, thanks for the talk. So you had this eta rule for these binary products, and I think there was also a slide saying that you also had this natural numbers in the type theory as well, just to check that nothing sort of breaks. Do you see these techniques working for cases where you have infinite data structures with eta rules? So the example I'd be thinking of is something like a vector type, where maybe if you know you have a vector of length 1 plus n, you can know that's always a cons form or something. Do you think, I don't know, maybe there's more canonical examples, but do you think the same techniques should work?
I guess I don't. I wonder if you can elaborate, like what's the thing that you think would make, like I don't see like how vector would be like fundamentally different from nats, because natural numbers already is an infinite data. Like the only complexity that vector adds, I guess, is like indexed by the length, which can make things a bit tricky.
I didn't have a specific problem in mind, just that there's sort of the inductive infinite structure going on at the same time, but no, it was more, have you thought about this at all?
I guess not really. Like we're really like only like I think from a theoretical perspective, like sort of having nets and assuming we also add like equality type. I think that the sort of expressive power from a theoretical point of view should be enough to like even encode vectors. But I think it is in fact I think an interesting question to consider, like how to deal with the more general inductive types. I think this method should be compatible, although as far as just from looking at the Meta Rock project, there's lots of weird issues that can pop up when you consider the more general cases. But I think with vector in particular, just encoding it in the sort of minimum form without considering general inductive types, I think that at least should be perfectly fine. But then
Thank you.
I haven't tried actually doing it, so I can't say for sure.
Let's thank our speakers then.